Here we go. Our topics. We're going to explore exponential and log equations and applications. So I'm finally going to teach you, like, how do you find that power that's kind of like in between values, you know, like 2 to what power gives you 3, you know, something like that. So our objective is to solve exponential equations, then we'll solve log equations, and then put them together in some application problems, okay? So for today, it's just a lot of examples on how to solve these equations. Here we go. So quick definition. An equation that contains a variable in the exponent is called an exponential equation. Okay, so some examples underneath it. Two little examples, and we're going to be solving those, by the way. We're actually going to jump into it. But anything when you have an exponent that has a variable, it's an exponential equation. These are kind of fun to solve. Once you get the pattern and the rhythm down, you'll see like what we can do to isolate some things and make it easier to work with. Okay, so this is going to lead us into what's called the equivalence property of exponential expressions. If b, x, and y are real numbers with b greater than 0, and it can't be 1. Again, just kind of using the same components when you're talking about exponential equations. Okay, then b to the x equals b to the y implies that x has to equal 1. Okay? Which makes sense. If you have the same base, then those exponents have to be equal to each other for that whole thing to be equal to each other. There's no other option. All right? So let's try it out. So solve. So let's say it had something like 36 to the k minus 2 equals 216. And I want to figure out what k is. Now I suppose that you can guess and check. Can you find values of k? You subtract 2, raise 36, and see if you get 216. Yes, you could. Not the most efficient way, right? So how can I use this property to solve this maybe a little bit more efficiently? Okay. Well, first I'm going to come up with the same basis. Okay. So here's what I would put as a step. So rewrite one or both sides of the equation with the same base. Okay, and that varies from problem to problem. So for this one, well, I could rewrite those as a power of 6, both of them. Okay, I'll use a different color here to help so we can see this. So 36, well, that's 6 to what power? Second. Okay, so let me rewrite this. So it's 36 can be rewritten as 6 squared, and then we'll raise it to the k minus 2 power. Now notice, if I were to simplify it, I get the original. That's how you know that you're still doing something correctly. So again, if I were to take 6 squared, which is 36, I get this. And then this guy over here would just be 6 cubed. So get them as that. Okay, your next step is to simplify anything that's remaining. And when I mean simplify, look at what I have over here. Okay, I could simplify it a little further. Power to power, when you do exponents, you multiply, right? So this whole thing becomes 6 to the 2k minus 4 equals 6 to the third. Now, does that always happen? No. You might actually just have nothing here and just have k minus 2, and that's fine. But in this case, I have to simplify. Now that they have the same base, well, using that property over there, I could say that the exponents have to be equal, right? For that to even work. So now for your last step, set the exponents equal to each other. So 2k minus 4 equals 3. And just solve. So we'll add 4 to the other side. So 2k equals 7. And we get, well, k is equal to 7 over 2. So my solution set, I should write this formally. So solution set is just 7 over 2. Again, could you have gotten to that point by guessing and checking? Maybe. Maybe not. But this is a lot more efficient. Okay? Any questions on that? Does that make sense? So again, just rewrite it as the same base. And that varies depending on, well, what your original values are. Okay? Just have to figure out what it is. All right. Now, let's say this happens. So now let's consider the case when we can't have a common base. Okay? So in this case, I had 6 and 6. That was beautiful. That was able to work. If I have 5x to the equals 50, well, if I try to change it, I get 5x equals 5 to the what? So 5 to what power gives me 50? I don't have anything. So, womp womp. Not good. Okay? So how can we still solve something like this, right? Because it is still solvable. There is a way for me to actually do this. And we're gonna get there with a little help of logs, okay? So let me write down some steps here on how we can do this. So steps to solve exponential equations by using logs. So if you're a person who likes to have steps, this will be good. Good to write down. So your first step would be to isolate the exponential expression on one side of the equation. Okay? So if you look at the thing I just did prior, that's isolated. I don't have like 5 to the x plus 1. If I did, I had to subtract the 1 over. So no matter what, isolate it. Okay, now step 2. Take a log of the same base to both sides of the equation. And I'm going to underline that. That's important. So log of the same base. Okay? That could be base 10. That could be base E. That could be base 2. Whatever it is. Okay? And we'll talk about like how do you know which one to use in a moment. 3. Use the power property of logs to bring down the exponent, which is helpful because what that's going to do is allow the exponent to be no longer in the, or the variable in the exponent to be actually in front, okay? No longer trapped. And then your last step is just to solve. Solve the resulting equation. Okay? the steps we're going to take with this example. Solve. 9v equals 48. We could estimate. We could say, well, 9 to the first is 9. 9 squared is 81. So it has to be between, well, 1 and 2. That's all we got. So can we come up with an actual solution to this? Absolutely. Bless you. So the first thing, is this exponential part by itself? It is, right? There's no +1, there's no number in front of this. It's all good. So step 1's cleared. Okay, step 2, take the log of the same base to both sides. Okay. Now notice, I don't really have anything in particular, like take log base this or that. What I'm gonna do is just keep it very generic. I'm gonna take log base 10, all right? We know common logs, even with change of base formula stuff, it works nicely. So that's what I'm gonna do here. So I'm gonna take the log base 10 to both sides. And you're gonna be doing that a lot, base 10. You could have done the natural log, and we'll look at one of those in a moment. So this is gonna be log, okay? 9v equals log 48. Now because it's base 10, I'm not gonna write the base underneath it. We know that if there's nothing written there, it's assumed to be a base 10. So now looking at that third step, we're gonna take the power property of logs. Okay? So that's this guy. So we know that if there is a power here, that's the same thing as bringing it out in front. So this is now v, log base 10, 9 equals log 48. Okay? So just bring the exponent down. And then we're on the last step. If you look at the far board over there, solve the equation. Solve what's left. So if v is being multiplied to this, the opposite would be to divide. So divide both sides by log 9. So my answer is log 48 over log 9. So I guess I should put it in nice curly brackets, right? Make it official. That's my solution. Now that's an exact solution, right? Because I'm not rounding anything. I'm letting the person have all those digits. But if you typed in your calculator, okay, I'll put an approximation here. You get 1.7619. Okay. So that's the power. And you can check your work. I'll put it over here. So if you want to check, okay, you could do 9 to the 1.7619 power. And it does get close to 48. It is approximate. And the reason why it's approximate is because you are rounding if you just use that. Okay? If you raise it to this whole entire thing, which keeps all the decimal places and all the values to it, you'll get more exact to 48. Okay? Any questions on that, on how we did it? So again, I just took base log 10. Could you take the natural log to both sides and get the same conclusion? Absolutely. You just want to pick something that's easy to work with. And I tell you what, there's one more. So you see the 48 and 9? If you want, okay, and you might see this in textbooks as well, they'll use the change of base formula and rewrite this as log 948. So this is using the change of base formula. So you could rewrite it like this. So just in case, I don't want people to look at it and say, I didn't get the same answer as that. They're just using the change of base formula. Okay, so those are equivalent to each other. Just in case if you see it. All right. Let's try another one. Same instructions, we're going to solve. Let's see. We'll do two of these. So let's do 12 to the -9n minus 4 plus 8 equals 88. And then over here, I'll do 10 equals 2e to the -0.1t. So I'm going to show you a couple other ways to approach these now. So the first example, I just use base 10. But for these examples, I'm going to do something a little bit different. The good news is you have a choice, okay? So if your work looks slightly different than someone else's, that's okay. Get the same result. Okay, so let me just kind of divide the board here so it's easier to see. So for the first one, kind of like looking at these steps over here, I want to isolate the exponential part. So that 8, that's got to go. So we'll subtract 8 to both sides. So I get 12, negative 9 minus 4 equals 8. Okay. Now we take the log to both sides, right? And instead of doing log base 10, what I'm going to do is do log base 12. Okay. Now why am I doing that? Watch what happens. So over here, I'm just going to make a note. Okay. So I will take log base 12 to both sides. Okay. It's going to help me simplify things a little quicker than just doing base 10. So here's what's going to look like. So log base 12, 12 to the negative 9n minus 4 equals log base 12, 80. At first, it looks like, why'd you do that, Mr. McCall? This one over here looked a lot nicer. Well, it's going to look nice because look what happens. Don't these 12s just kind of go away, right? You just get what's in the exponent. That's one of our properties here. So we get negative 9 minus 4 equals log base 12, 80. Okay? And now we just solve for n, like a normal equation. So I'm going to add 4 to the other side. And then my last step, divide by negative 9. Okay, there's my answer. Now this does, and like I said, if you want an actual approximation, negative 0.6403. Okay. Again, not something you'd probably figure out on your own just by guessing and checking different things like that. So having these things in place really helps. So any questions on that? So again, I just gave you 2 different ways. So over here was base 10, which works out really nice. Plus it's probably easy to type in the calculator, right? But if you wanted to, you could take base 12, okay, and get your solution that way. Alrighty, now over here, we have an e. So immediately, here's what I'm thinking. If I do the natural log with the base e, do you see how the e's might help cancel some things out? So immediately thinking about this, I have an idea in my brain, like maybe natural log would be the easy one to work with, okay? So let's do that. So first things first, is this by itself yet? Not quite. I have a 2 out here. So let me divide both sides by 2 first to get the exponential part by itself. So I get 5 is equal to e raised to the negative 0.1t. Okay? Now I'll put this in blue here. So I'm going to take the natural log to both sides. Why the natural log? Because it has a base e, and that'll help the right-hand side get simplified a little bit easier. You don't want to do like a normal log base 10, then you have a lot of things happening there. Makes it more complicated, doesn't really help things. So it'll be ln of 5 on this side, ln of e raised to the negative 0.1t. Well, we know that this is a base e. So e to what power gives me this? It's just this guy right here. So we have ln of 5 equals negative 0.1t. Okay? And just to give you a side by side, that's the same thing as me doing this over here, right? The argument and base were the same. There's an e here. I don't write it, right? It's invisible because we use this symbol. But e, they're the same, so you're just getting the power up there. Okay, hey, we have one more step to go. Just divide. So we get ln, natural log of 5, divided by negative 0.1 equals t. So that's my solution set. I guess I didn't do the curly brackets down there. I'm slacking. I think I just ran out of space, that's why. Not so much slack in there. So that's my official answer. But if you actually wanted a decimal to this, well, I got you covered. negative 0.16094. Okay, so that's the power that you would use for those to be equivalent to each other. Okay. All right. Any questions? Don't get overwhelmed by, you just want to pick a method, okay? And this is the weird part. My method, I like taking natural log. Log has 3 letters, that has 2 letters. I like writing 2 letters instead of 3. That's a bad reason. But natural log, I find it's easier to work with. But again, you have 3 different kind of variations there. Just pick something that feels comfortable to you. All right. Let's try another example here. Let's keep this going. Let's do 3 to the 3x minus 1 equals 2, 3x plus 9. Now we shifted some things a little bit, okay? So notice that we have 2 bases that are not the same, okay? Over there we had just 1 base to work with. Now we have 2 bases. So now it's like, what do? Well, you don't do anything different, okay? Isolate as much as you can, which I get nothing to isolate. Now take some log to both sides. I already told you I think it's easier to work with natural, so I'm gonna use natural. So I pick the natural log for this one. So, I pick, let's English well here. Sorry, English good. I pick to take ln to both sides. The reason why I put the words I pick is that way you guys can actually see that you made that choice, okay? So here we go. So we get ln 3 to 3x minus 1 equals ln 2 to the x plus 9. All right. So far, so good. So now because this is a power, I can bring it out in front. So I get 3x minus 1 ln of 3 equals x plus 9 multiplied by ln of 2. So that's just using the product, or not product, power property. Okay. Well, doesn't look like it got any easier, huh? So what do we do next? Because it doesn't quite follow what we've found out over there, right? Well, here's what we can do. It's going to look a little messy at first, but it will clean up nicely. I'm going to take this natural log of 3 and distribute it to both these terms. Take the natural log of 2 and distribute it to both of these terms. Okay? That's what I'm going to do. So here's what it's going to look like. I get 3x, natural log of 3, minus 1, but I won't put the 1 there, natural log of 3. So that's me distributing the left-hand side. On the right-hand side, I get x, ln of 2, plus 9, ln of 2. Okay? Be careful, you're not multiplying the arguments when it comes to these. You're only multiplying the whole thing by what's in the parentheses. Okay, I'm trying to solve for x, right? One of the things I noticed is that this term has an x and this term has an x, right? So let's group them together. Then we go and factor that out. Does that make sense? So in this step, I would group your x terms. Okay? So that means, let's do this. I'm going to subtract this over here, and then I'm going to add the natural log of 3 over here. So I'm going to do 2 things in 1. So again, this is what I'm going to do. I'm going to take this bad boy, move it over here by subtraction, take this guy and add it over to the other side. Okay? So I get 3x, natural log of 3, minus x, natural log of 2, equals 9 natural log of 2 minus, oh, not minus now, plus the natural log of 3. Okay? So I did 2 things in 1 step. Just to save some board space, because as you can see, I'm kind of running out again. A big issue. Now, on the left-hand side, I got terms with x's in it. So that means I can factor that out. So factor an x out. I get 3 natural log of 3 minus natural log of 2. I'll rewrite everything else over here. And then to simplify, to get x by itself, x is being multiplied by all this, so the reverse would be divide. So divide both sides by what's in the parentheses here. So those cancel. I shouldn't say cancel, but it reduces to 1. Okay. So now my final result, so x is going to equal, let's see if I can rewrite this, 9 ln of 2 plus natural log of 3, and then down below, and yeah, I had space. Nice. There's my solution. Now if you want a decimal, I'll put that underneath there as well, but there it is, 2.8190. So if you were to plug this into the original, those two things would be equal to each other, which is pretty darn crazy. All right. Any questions? So far, so good? Okay, we're going to keep doing more examples. And put it this way, I'm trying to give you a variety. That way, when you guys try this out for tonight, you have a good guide. You have a good resource where you could look at all these different examples and think, okay, which one kind of matches what I'm looking at here? Okay, so let's try an exponential this time. But we're going to have to use a little bit of quadratic form for it, okay, as a way to solve it. So we're going to bring back quadratic form just for a little bit. So same thing, solve. So e to the 2x plus 2e to the x minus 48 equals 0. Okay? Now, one of the things to notice is that looking at these last couple examples, I can't really isolate anything. I don't have that capability. But one of the things that kind of screams out to me is e to the x is something they have in common, these two terms. And I could rewrite this to where there's like a square term, like a quadratic term. So let me rewrite this part right here. So this is the same thing as e to the x raised to the second power. That's equivalent. Okay? Plus 2e to the x minus 48 equals 0. That kind of looks like a quadratic to me. So what I'm going to do, because I don't really care about e to the x right now, I'm going to let u be e to the x. I'm going to clean this up a little bit to make it easier to solve. And I'm going to substitute. So this is now u squared plus 2u minus 48 equals 0. That's a lot easier to figure out than what I had originally. Because now I could just use all kinds of methods to solve that quadratic, right? One thing that we got to be careful with. Okay, e to the x. If you think about what that graph looks like, that's a quadratic. How many answers does a quadratic have? Potentially. 2, right? You can have 2, you can have 1, you can have 0. So when we're done with this, if we get 2 answers, we better make sure we check them, right? Because it's not guaranteed that it's going to match this, because these are 2 completely different things. So even this is going to help me solve for answers, all the answers for this works for this guy, but it might not necessarily mean it works for the original. So we have to be careful with stuff like that. Here I can solve by factoring, right? So let's do that. Let's do 8 to negative 6. That gives me negative 48 too, right? Solve each one. I get u to be negative 8 and u to be 6. Which is fine. Again, they might not both work because we're talking about an exponential, but those two work for that quadratic. So now what do we do? Well, I'll put down here, plug back into your u substitution. Okay, that's this guy up here. Now I don't know what u is, I gotta translate it back to what the problem was originally. It's like one of those temporary things like, oh, this was so nice to work with. Now let's see how it looks at the original. So I get negative 8 equals e to the x. Now let's stop there for a moment. Is that possible? Can you raise a number to a power and get a negative? No. So guess what? Not the fun. So negative 8 is out. Okay, over here we get 6 equals e to the x. Okay. And there's nothing undefined about that. That's okay. Now, how do I solve for x? Let's look back over here. We can use these methods, actually, use something like this even more specifically, this example, to solve for x. So I'll take the natural log to both sides. So the natural log of 6 equals natural log of e to the x. Same property as before. This has a base of e, arguments e, so it's just the exponent is the answer. So ln of 6 equals x. There we go. So we found it. Now let me give you a decimal approximation. Okay, and I would encourage you, like, sometime today, try and plug those in your calculator to see if you don't get decimals. If you don't, let me know. That means you're plugging something in wrong. Okay. Now you should check, and in this case it does work, but I'll put a little note here just to save some time. But always check still. Okay? Because it might not work. You might actually have a no solution problem. That can happen. Okay? In this case, I can tell you definitively it does work if you plug that back in. All right. Doing pretty good now. That's a lot. That's a lot of examples. Any questions so far? We okay? All right. Feel free to stop me if not. Okay. Definition. An equation containing a variable with a log expression is called a log equation. Imagine that. Gotta love math definitions. So let me give you some examples underneath it, just so you have something in place. Now we have some logs, but now the variables are inside of it. So we're going to see how do we mess with those guys now. And to be honest with you, it's not that bad, okay? If you look at this guy here, this is going to lead us to one of the properties. See how they have the same base, right? So if they have the same base, the only way these are going to be equal to each other is if their arguments are the same. So you can essentially just set the arguments equal to each other and solve. You're done. Okay? So let's write this down. So we call this the equivalence property of log expressions. If b, x, and y are positive real numbers with b not being 1, then log bx equals log by implies that x equals y. So it's very similar to the very first equivalence property I taught you at the very beginning of this lesson, just with logs. So let's do an example. Log base 4, x minus 3 equals log base 4, negative 2x plus 9. Now I'm going to circle this. Because they have the same base, then the arguments have to be equal to each other. That's the only way the whole expressions could be equal. So therefore, I could set x minus 3 equal to negative 2x plus 9, and just solve for x normally. Okay, nothing tricky about that. So I'll add 2x over. I get 3x minus 3 equals 9. We'll add 3. We get 3x equals 12. And then that gets us to be x equals 4. Okay. Now, it would behoove you to do this, okay? I kind of led to it over there, but I'm going to show you here, okay? You do want to check your work with it. So for instance, if I do log base 4, 4 minus 3, equals log base 4, negative 2 times 4 plus 9, we're hoping those are going to be equivalent to each other. Now here's the good news. You don't need to have a calculator for this, okay? The only thing you're focused on is this. Do the arguments equal to each other? Because they have the same base, so that's all you have to worry. On the left-hand side, you get log base 4, 1. On this side, we get log base 4. Well, that's a negative 8, plus 9 gives me 1, so I'm good. Those are the same. All right. Okay, so far so good. Now, let me give you an example where they don't work, okay? So let's do one of those. You know what, let's put this in parentheses. Not all solutions work. That way, if you need to look back in your notes, you know which example had something like that. Okay, so here we go. Natural log of x, natural log of x plus 15, natural log of 34. All right, now, first things first, let's clean this up a little bit. Let's use some properties of logs to where we have an actual, like, something on the left, something on the right, because there's too many things happening on the left-hand side. So because we're adding them, one of the properties of logs, addition is the same thing as what, multiplication, right? So let's condense them. So let's make it the natural log x times x plus 15 equals natural log of 34. Okay. Now, if you take a look, because these have the same bases, which is base e, the arguments have to be equal to each other. So let's go ahead and set the arguments equal to each other and solve for x. So again, just kind of go back to the original. You might have to manipulate some things a little bit first before you start setting arguments equal to each other. In this example, I didn't have to do that. Everything was already simplified. I could just go ahead and start solving for x. So I get x squared plus 15x equals 34. I can tell I have a quadratic, so let me go ahead. I'm going to move the 34 over and set it equal to 0 and solve. And I try to create problems where they factor nicely. And you're going to see that as well when you guys practice this. I try to make sure we still keep with that theme. So for 34, negative 34, it'd be 17 and negative 2 would be the factors. So x plus 17, x minus 2 equals 0. And I get negative 17 and 2 as my potential solutions, right? Because think about it. It is a natural log, right? We know what the graph looks like. It's not the same thing as a quadratic, so we have to be mindful of it. So down here, now check. Now check them. Okay? Make sure they work. Now here's the good news. You can figure out really quickly if one of them doesn't work. You have negative 17 here, right? Will negative 17 work for the first term? No, you can't have a negative argument, right? So already I know negative 17, nope, not good. But over here, let me just make sure we write that out. So let's say x equals negative 17, give it a frowny face, and we'll put next to it y. ln of negative 17, that's undefined. So there's no reason to go further. And the other ones work too, right? Like look, negative 17 plus 15 is negative 2. Again, not defined, so we're done with that one. Okay, now x equals 2, let's see. So we get ln of 2 plus ln of 2 plus 15. Does that equal ln of 34? At first, it might not look like it, but we're going to use the property of logs to actually show that this works. We get ln of 2 plus ln of 17 equals ln of 34. Now notice, because we're adding them, it's the same thing as multiplying the arguments together. So 2 times 17 is 34. So we're good. So this only had one answer, and that answer is 2. Okay, any questions? Yes?
In like the first step,
Mm-hmm.
this second one, how did you go from ln x plus ln to the next part?
From here to here? So here's the deal. I use the properties. Okay, one of the properties of logs is if you're adding them, it's the same thing as combining them and just multiplying your arguments together. Okay, so it just goes back to those properties I taught you in the last lesson. Yep. And one of the things I know in the last lesson, we talked about just normal logs, but natural logs follow those same properties as well. Okay. We're just about there. You're in the end now. So now we're going to solve log equations by using exponential form. Okay. So let's do an example. So we're going to solve log base 9 x plus 4 minus log base 9x equals 1. Okay. Now, here's the unfortunate news. If this 1 wasn't here, let's say that was a 0, I can add this log to the other side. You got the same bases, set the arguments equal to each other, you're done. But that 1, man, that 1's annoying. So I can't do that. So instead, let's try to combine these into one log, okay? So because it's subtraction, that means it's the same thing as what? Dividing those guys, right? Okay. So let's go ahead and use that property. So we have log base 9, x plus 4 over x equals 1. So that's me using the properties. Okay. Now, I kind of lucked out here. So here's what I can do. I'm going to put here in blue. Now, rewrite in its exponential form. Okay? Which is what we did at the very beginning, like, practicing what that is also equivalent to. So that's the same thing as 9 to the first power equals x plus 4 over x. Now we just solve for x. So I can multiply both sides by x. So we get 9x equals x plus 4. We'll subtract the x over. And then divide. And I get a half. Now we should check, make sure it works, and it does work, okay? Just save a little bit of time, but this is a good answer. So my solution set is going to be a half. All right. So the last thing we got to do, guys, is just the application problems. But up to this point, any questions? Again, a lot of different examples, not trying to overwhelm you, I'm just trying to give you a good variety, that way you're good to go. But for this part here, notice that when I first looked at it, I was like, okay, there is a property here I can use, and then if I rewrite it, oh, okay, now I can start finding x. So your first attempt at something might not work, and that's okay. Nothing to be frustrated about. Just, save your eraser, just cross it out. Go back to the drawing board and think about what other things could I use to solve this. All right. So here's some applications. Suppose that that you invested $3,000 in a bond fund. The expected yield, meaning the percent, is 4%. And the earnings that you get from this, if I can spell that right, are reinvested quarterly. Okay. So for part A, we're just going to start by writing a model to represent the situation. And then for part B, we're going to determine how long it will take the initial investment to triple. Okay? Which is always good. If you're trying to invest something, you kind of want to know how long it's going to take to get a certain dollar amount. If you can't do that, then you might be investing poorly. Okay, so we're going to go back to those equations that I taught you, I don't know, it was a lesson or two ago, in terms of compounding and account balances and so forth. So account balance is going to equal your principal, which is 3,000, 1 plus your interest rate, 0.04, over how many times you're compounding. For us, it's 4 times, raised to the nt, which would just be 4 times t. And again, those are some things you do have to memorize in terms of the formula. So up here, if you need a refresher, there's the formula for you. Okay, so that's what we're using for it. So there we go. So that represents this specific problem. Now part B says, well, how long does it take to triple it? Well, now I'm going to solve for t. And originally that would be an impossible task, but now that we have a lot of this background, we have a lot of these different techniques to help us, we can solve for t now. Okay, so if it's going to triple, and I start with 3,000, what am I going to end up with? 9,000, right? Okay, so let's put 9,000 as your account balance. Equals 3,000, 1 plus 0.04 over 4, and then 4t. Okay. And a goal, and again, our goal is to solve for t. So far, so good with that? Now, what do we do? Well, think about what we did at the beginning. We had to isolate the terms that had the exponent, right? So that 3,000's there. So why don't we just go ahead and divide both sides by 3,000. Okay, that way we're trying to isolate this as much as possible. Good news is, look what happens. We get 3. That's a little nicer to work with, huh? And then 1 plus 0.04 over 4 raised to the 14th power. Okay. Now, next I would take some log to both sides, right? And again, my preference is natural log because I think it's easier to work with. So I'm going to take the natural log to both sides. So this would be the natural log of 3 equals the natural log of all this stuff. Again, running out of space. Maybe I was too naive to think I could fit this all on this board, but we'll see. I'm going to try. Now, looking at the right-hand side, because this is raised to a power, that's equivalent to me, writing this out in front. That's that property we've used. So we have the natural log of 3 equals 4t, natural log of everything in the parentheses here. And let me just highlight or circle, just keep it in mind what we're trying to solve. We're trying to solve for t, right? We don't want that to go away. So my last step, I have a 4 and a natural log. That's multiplying the t, right? So the opposite of multiplying is dividing. So what I'm going to do is divide everything by 4 natural log of what's in here in the parentheses. Okay, so both sides is being divided by that. So that cancels out here. And then what I have left, grand finale, but here it is. Let me get rid of that swoop. There we go. So this, man. There we go. Is the time it's going to take for it to triple. Now you're probably thinking, well, that's great, but I'd rather have a decimal. I don't blame you. So if you type that in your calculator, okay, I'll put it over here. The time it's going to take to do that is 27.6 years. Okay? So that's how long it's going to take to triple its value. Okay? Any questions on that? All right, you guys are golden. That's it. Okay, so that's us solving a bunch of equations with logs. So tonight when you guys practice it, again, don't get overwhelmed. You have all these examples that you can look through now, okay? And just figure out what example kind of matches the situation you're working with. And pick a log that works.